So in this video, we're going to look at the derivative, and then we're going to look at a way we can express it that might be a little different from what you're used to seeing. So this here is what you'll see in most beginner calculus textbooks. The derivative denoted f prime x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. So what is the derivative? Basically, we can look at the derivative as the slope of the curve. So I've drawn just some random function right here, and we want to find an expression f of x that tells us the slope of the curve, or also you can call it, it's the tangent line of the curve. So basically at this point x here, we're looking for the slope that just touches at this point of tangency here. So knowing that, where does this come from? Well, this just says the slope here, if we extend this x by a small amount to x plus h, we could get a slope here just by plugging in x plus h and f of x plus h to be a 1 point. And then we could find the slope of that, which is going to be f at x plus h minus f of x, that's the rise, and the run is going to be x plus h minus the x, which is just going to leave us the h. So that's how we get this expression here. And it's h going to 0 because I've drawn h to be this amount here. But as h gets smaller, remember it's going to 0. We'll keep moving along here and we'll keep finding the slope from here to here, and then here to here, and here to here. And as we get closer and closer, what we'll get is the tangent slope. Okay, so now let's look at this a little further and realize that this h here is just some value. But we could say, well, what about x plus 5h? Well, that would be at about this point here if we're starting with an h of this value. And that might look at the beginning like these points are very far apart, so it doesn't seem like a good approximation. But remember, the h is still going to go to 0. So as the h goes to 0, what will happen is we'll be taking points along the line that get closer and closer to what we want. And then as h gets smaller, we'll get back to here, and then h will continue to get smaller, and again, we will get our tangent line. So, and this 5, it doesn't have to be 5h, it can be 100h, it doesn't really matter. The point is, as h goes to 0, we will get this tangent line anyways. And here's the nice thing. We want to find the derivative at this point here, x. So we've extended it this side, x plus 5h or x plus anything h. We can do the same thing on this side. So maybe this is x minus maybe 4h or something like that. And now, even though we might be starting with a point here and a point here, and that slope might look far from what we want, we have to remember that as h is going to 0, we will be able to move along here, and these 2 points will move along here, and we will still get the tangent slope we're looking for right here. So we can transform this expression then to look like this. We still want the limit as h goes to 0. But instead of x plus 5h, you know, we could call this anything. So let's call it x, maybe, you know, some, let's just getting a little crowded here, but x plus some general point here, a can be anything, x plus ah. And over here, we could take x minus bh, where the a and b can be anything, as long as a plus b is not 0. What would that give us? It would give us the change in y, f of x plus ah minus f of x minus bh. So that's the change in y. And then the change in x is going to be x plus ah minus x minus bh. And then we'll notice on the denominator here, x minus x will cancel out, and so we'll just be left with ah plus bh. Okay, so what we're going to get is this result here. The limit as h goes to 0 of f of x plus ah minus, this should be a minus, minus f of x minus bh over a plus b h. This is also the derivative for all a and b element of real numbers such that a plus b is not 0. So we can choose any values we want, any real values for a and b. But the thing is, we just have to be sure that whatever pair of values we choose for a and b, that they do not sum to 0. Okay, so let's look at a specific example. I've chosen a specific function here, f of x equals x squared. And if you work out this way, we'll get f prime x, the derivative is equal to 2x. But let's use this way to get the same result. I'll leave a and b as general, and we'll use this function here. So still the limit as h goes to 0. F of x plus ah, we just plug in x plus ah here for x. So we get and then plugging in x minus bh. Okay, so now we have to do a little bit of messy algebra. So here, expanding the bracket, x squared terms will cancel out, and we'll just be left with so here we can factor out an h. So we get this, and now we can cancel the h's and simply plug in h is equal to 0 in this expression here. We only have h here and here. And plugging in 0 will eliminate these terms, and we'll just get the limit as h goes to 0 of 2xa plus 2xb. So we'll get that. Actually, we've plugged in the h, so the answer is just this. And then we can factor out 2x. So we get this, and then remember, this transformed version of the derivative only works if a plus b do not sum to 0. If they sum to 0, we'll just get a 0 over 0 expression. So here, a plus b over a plus b, we can cancel those, and we just get our 2x. So you'll notice, obviously, this is a nicer expression than, having a be 100 and b being 1,000 or something like that. But if we plug in a equals 1 and b equals 0, which is fine because 1 plus 0 is not 0. But if we plug in a equals 1 and b equals 0, we just get this, this familiar expression here. So that's all for this video. Thanks for watching.